Hello everyone, I'm Ahmed Khalifa. I'm a PhD student at NYU. I work with Professor Julian Tigelius, and today I'm going to talk about our research, which is the tree search. Keep in mind, it's still work in progress. So what is the tree search? So the tree search is a framework that allows us to express different tree search algorithms. So what does this mean? So it's this framework where you can describe using a certain language what's your tree search algorithm, and it will return you a model where you can use it to run it on your problem. So why? Having a unified language for tree search algorithm will create this space where we can express variants of algorithms, and if we have a space we can use a search algorithm to try to find algorithms for certain problems that perform better than the current ones, and we can find new algorithms that never been discovered. Also, if we have this unified language and we can express in it different algorithms, we can measure similarities and differences between all these algorithms, and by doing that we can have more understanding about these algorithms and why they perform better on certain problems than others. Also, if you at any time felt I have this idea of the tree search and I want to try it, so you can just open and then write the description for it in the language, and based on that it will give you the model and you can test it and see if your algorithm is good or bad. Before I continue, I have to describe what is Monte Carlo tree search. So Monte Carlo tree search is a tree search algorithm that use Monte Carlo simulation instead of evaluation function. And this slide shows the 4 main steps of the Monte Carlo tree search. It's a very popular slide and you can find it in all the papers that refer to Monte Carlo tree search. As you can see, the Monte Carlo tree search consists of 4 main steps: selection, expansion, simulation, and backpropagation. The selection is the first step where it tries to select what is the next node in the tree. So if you are at the root and you have all this node underneath you in the tree, try to find which one it should explore now. And it goes selection until it reaches a node that's not fully expanded. For example, this node that it reached is not fully expanded, and when it reaches it goes to the next step, which is expansion, where it creates this new node and place it in the tree. After that, we go to the simulation step. In the simulation step, instead of using a heuristic function, it runs Monte Carlo simulation until it reaches a terminal state, and then it sees if this terminal state is good or bad, and then it goes to the next step where it backpropagates this information back through the nodes that have been visited. So our research is based on the Monte Carlo tree search framework. We use the same framework, and this is because Monte Carlo's tree search framework is very flexible. If you change, let's say, the selection step, instead of using the UCB1 equation, and you always explore the shallowest nodes. By doing that, we have kind of breadth first search algorithm. So in our tree search, you can customize each step in the Monte Carlo tree search framework using mathematical expressions, such as 1 over the depths, or just explore the most visited node right now. Different, you can write whatever you want. For the selection equation, so our framework will apply your mathematical expression on all the children that it's gonna select from, and then we'll pick the maximum one, which is exactly similar to the Monte Carlo tree search. And the next step is the expansion. We use 2 equations instead, or expressions instead of one. We have the partial expansion expression and the expansion expression. The partial expansion determine if we want to still expand or not like the Monte Carlo tree search, where it just, when it visits a node that's not fully expanded, it expands. By using the partial expansion, we can alternate between should we expand right now or should we continue selection. And the other one, which is the expansion, it's similar to the selection one, where it applies to all the unexpanded nodes, and based on the value it will pick which one is going to be expanded next. Next step is the simulation. In simulation, we have 2 cases. Since not all the problems you have a terminal state, and your Monte Carlo simulation won't reach this terminal state. For example, in Mario, you can always press left, right, left, right, left, right, and you never reach terminal state. So we supply two expressions. The first one is a stop expression, where you can write an expression that tells the algorithm when it should stop. Maybe it's based on time, maybe it's based on like number of iterations. After that, stop. The other one is the simulation action, where it uses it to pick which is the next action to play. If you want the random one, you can just add random number here, and when you add a random number, this means just pick any of the actions. It doesn't matter. After that, we go to the back propagation. So our system allow you to like define your own variables. You can define whatever variables, and all these variables will be held in every node in the tree, which you can access at any time. Also, like our framework have the like tree variables such as like depths, number of visits, state evaluation, which also you can access. But so in the back propagation, you provide the system with this mathematical expression where you can update your defined variables, like the ones that you defined at the beginning. Someone might ask, this a lot of expressions. Aren't these expressions will slow down the algorithm, especially if you are in a time-sensitive domain, like you are playing a game and you only have like 40 milliseconds to decide? Having all this expression to evaluate will slow down like the system. So we needed to see how like bad we can. So we use the general video game framework as a framework to test that. This framework, like you can have like more than 90 games, and you can describe new games using the video game description language. And it help you to integrate your own agent there and like use it and play around with it. And each agent is provided with a 40 millisecond, and after the 40 milliseconds, it has to reply with the current actions that it will do. So we made like an implementation of the Monte Carlo tree search algorithm in our framework, and we use the vanilla implementation provided with the general video game framework, and we run them over all the 90 games, and this is how the results. So as you can see, our like algorithm explore a lot less nodes than the native MCTS, and because of that, the average win and the average score is a little bit worse than the native implementation. Yeah, we know this like will be a problem, but we are trying to search the space to find new algorithms. If we can find new algorithms that outperform our slow implementation of MCS, this is a good thing. So in order to understand also how this framework is working, I made like an example over the BFS. And so first thing, these are the defined variables we have. We have the next node, and we have a locked variable. We define two variables, and I'm gonna explain them later in details. And then our selection will use this expression which says try to maximize the summation of the next node, and the locked variable like always picks the nodes that have the maximum. Then after that, for expansion, since the BFS is always expanding, so our expansion is just like a constant one, which means always expand. For simulations, there is no simulation, so it's 0. And the last thing, how to like the back propagation, where you update your own variables. So the next node, as you can see, it represents which next node I'm gonna like search. And since the BFS, so it need to search the shallowest node. That's why the next node for any node that doesn't have children is 1 over the depths, which means as the depth is smaller, this value is bigger. While when you back propagate it through the tree, when you are at the root, you don't know where exactly the branch that have the shallowest node. So you need to back propagate this value up. So that's why we used for the next node is the maximum children of next node. For the locked variable, so for the nodes that doesn't have any children, it doesn't matter, but for the parents, it's equal to 1 if any of its children or itself have unexpanded children. Like there is a node where it has at least one expanded child. It will be explained more with the example. So here's an example. We have the root node and the variables are like initialized with 0 and 0. After that, since we start the algorithm, it will try to expand because there is no selection. It cannot select anything. So when you expand, so let's say we expand the first one, so we initialize the values in it. So the next node will be 1 over the depth, and the depth is 2, so it's 0.5. And then we back propagate this value up there, and we update the variable. And since this node is not fully expanded, the log to became is equal to 1 in it. Then the next step, we start again from the root and we try to select, but since we say we always expand, so this means we expand the other child. And then we are back propagating it to the top, and as you can see, the log became 0 because all the children has been expanded. Because in this current problem, each node had only 2 children. So let's go to the next step. In the next step, since both are equal, it will select any of them. Let's say it's the left one, and after it do that, since it's not like expanded, it will expand a node out of it. And so the next node will be 1 over 3, which is 0.33, and then it will back propagate it to the parent. And since now it has one of the children expanded while the other is not, so the log became equal to 1, and it will update, go back and update the variable. And since the next node didn't change, because it always takes the maximum between the two next nodes, and 0.5 is higher than 0.33. Then the algorithm go back and from the root and go to select again. So the summation of the next node unlocked for like the left one is like 1.33, while the other is 0.5, which means it will select the left one. And after it selects the left one, since it's not fully expanded, it will expand it. So imagine if the log was not there, we didn't have it. This means that if we are gonna compare the two nodes to like select, which is the one on the left and on the right, 0.33 is less than 0.5, which means the system will go expand a node on the right one before it going back. It's still a breadth first, but we want to make our breadth first implementation exactly similar to the ones that use like a queue. So now we back propagate. Now the log became 0 and goes up. Then now, since the both logs are 0, the system will go to expand the one on the right. So it will select this node because it's highest as the next node, and then it will expand the action and back propagate it. So after that, we want to experiment and see if our framework can find new algorithms. So we use also still the GVG AI, and we decided to run like an experiment on one of the game, which is called like missile command, where you are the spaceship and you try to destroy all the fireballs before they hit the cities down there. And if you at least saved like one of them, you win. So we use genetic programming to evolve these like mathematical expressions. All the mathematical expressions were expressed as trees, and so our like mutations were like kind of like delete a node, add a node, switch a node to another node. But for our crossover, since we have multiple equations, we didn't make any subtree crossover. Our crossover is totally depending on just switching like equations. Like it switch between maybe the selection equation or the expansion equation, and see. We run the algorithm with 50 chromosomes for 50 generations. This is our fitness function. It consists of like 4 parts: agent, tree size, no error, and similarity. So the first one is the agent, which is the highest weight for it, because this is how the agent will perform over this game, over like 40 runs of the game. Next one is the tree size. Since we don't want like these mathematical expressions that's really complex and really big, so we are encouraging our like fitness function or our search algorithm to find mathematical expressions that are smaller in size. Also, it's like we are trying also to encourage not to have errors in these expressions, such as log a negative number. So by adding this term, just try to remove something like that. And the last term is the similarity. So the similarity from earlier experiments, we found that most of the chromosomes are trying to be like the best chromosome, and we wanted to discourage something like that, so we added the similarity metric to try to have a little bit diverse population with time, so not all of them like converge on like the best one, and that's it. So these are the results. We still didn't analyze them, but as you can see, like the one we find is far better than, it's not far better, it's a little bit better than Monte Carlo tree search algorithm. And it's exactly a Monte Carlo tree search with a new expansion equations and a different like backpropagation equation. We still didn't like analyze this equation and know why we perform better, but we need to do more like work and see if it's the reason behind that. So since it's a work in progress, so there is still a lot of feature work to be done. So the first thing is run more and longer experiments on different games, different problems, and see if our framework can find something that's like better than Monte Carlo research or A star or whatever that perform good in it. Second thing is the framework is still not documented, and I think there is might be some bugs in it, or it's a little bit slow. So we want to document and enhance the framework and make sure everything is seamless, so other people can use it and try to like and play around with it. Last thing is to publish a paper, because I'm a PhD student and I need papers to graduate. And thank you.